Alright, so in our previous tutorial, we look at how we can clean or prepare our data for analysis. In this section of the tutorial, I want to look at how we can start with exploratory data analysis. EDA or exploratory data analysis is one of the techniques used in analyzing datasets to summarize their main characteristics, often with visual methods. There are two main ways we can do this. We can either do this by data summarization or data visualization. Data summarization basically involves using numerical summaries and frequency tables to describe a dataset, while data visualization involves using graphs to describe a dataset. Okay, so in this tutorial video, we want to start with data summarization. Okay, so this is going to the second part. So EDA 1. Okay, so here I want to start with data summarization. Okay, so as I have already explained, data summarization just involves using numerical summaries and frequency tables to describe a data set. The numerical summaries does well for quantitative variables, while the frequency tables does well for categorical variables. So we'll be looking at some summary statistics. Okay, summary statistics for quantitative variables, right? And we also, so this should be 2.1.1. Okay, then we also look at some summary statistics for qualitative. So let me change this to qualitative or the categorical. Okay, so I want to start with summary statistics for the quantitative variables. So how do we summarize our data set using numerical summaries? We can use the summarize function. Okay, so summarize. This will basically help us to get a numerical summary for our variables. So we want to summarize sepal length. Okay, sepal width, petal length, and petal width. Okay, so these are the continuous or the quantitative variables. So let's try and execute this. Control D. Okay, let's go to our result window to see the effect. Okay, so we can see that in here we are getting some information with regards to the number of observations. We can also see the mean value, which is basically going to describe the center of our distribution. Right, the standard deviation is basically going to describe the variability in our data set. We also have the minimum value as well as the maximum value. Okay, so this is basically giving us some descriptive statistic, but we want to basically get more detailed descriptives for each variable. Then we have to use a new command, or let's say add some code into it. So let's add a detail. Let me copy this and add a detail function. So once I execute this, I'm going to get the discrete statistic for each of the variables in detail. Okay, so Control D. Let's flip to our result window. So we see that this is giving us the discrete statistic. Okay, some numerical summaries for the petal width. If you scroll up, okay, let's scroll up. You see that of petal length, that of sepal width, and that of sepal length as well. So we are getting the number of observations, the mean value, which which basically talks about the center of the distribution. The variability on data set is also catered for by the standard deviation. Okay, you can also look at the variance as well as the skewness and the kurtosis. The skewness is basically a measure that describes the degree and direction of departure from symmetry. A distribution is said to be symmetric if the left and right hand side of the distribution are the same, right, when you compare to the center value. Okay, And with kurtosis, it basically describes the thickness of the distribution in our data set. Basically, we are looking at how heavy or light the distribution will look like. Okay, so according to literature, if you have a skewness that is less than 1 or greater than 1, then it means that the data is highly skewed. Okay, and if the skewness is, let's say, around 0.5, minus 0.5 and positive 0.5, then we can say that um, the distribution is nearly symmetric. Okay, with kurtosis, if a distribution with kurtosis equal to 0 or approximately 0 will be is said to be mesokurtic. Okay, but this is just the kurtosis coefficient. In most cases, we use the SS kurtosis. With SS kurtosis, you are supposed to subtract 3 from the kurtosis coefficient, okay, in order to get the SS kurtosis. The SS kurtosis is basically used in comparing the kurtosis coefficient and with that of the normal distribution, okay. So in the case where the SS kurtosis, that if you subtract 3 from this coefficient, and let's say you are getting a value that is less than 0, then the distribution is said to be plateautic. Okay, that is the thickness of the distribution is basically flat and spread out. Okay, now if you subtract 3 from this, and let's say you are getting a value that is greater than 0, then the distribution is said to be leptokurtic, which means that compared to a normal distribution, the thickness of the distribution is basically high and thin. Okay, so we'll be looking at this as we proceed in our subsequent tutorials. We also have information with regards to the percentiles. Okay, the 25th percentile is the same as the first quartile. The 50th percentile is the same as the median value. The 75th percentile is the same as the upper quartile. So basically, if we divide our data set into two equal parts, 50% of the observation is basically less than 5.8 centimeters, and 50% of the observation is basically greater than or equal to 5.8 centimeters. Okay, with regards to the third quartile or the 75th percentile, we know that 25% of the observations are basically greater than 6.4 centimeters, while 75% of the observation are less than or equal to 6.4 centimeters. So we can interpret this as, let's say, the top 25% of the sepal species plant increases in length than 6.4 centimeters. Okay, and with that of the first quartile or the 25th percentile, we know that 25% of the observations are below 5.1 centimeters, while 75% of the observation are greater than 5.1 centimeters. So with the interpretation, you can also say that a single species plant of the sepal chosen at random has a 75% chance of increasing length than 5.1 centimeters. So basically, we have the software can basically give us the result, but at the end of the day, your ability to interpret this result is very important. Okay, so this is basically with the numerical summaries for the continuous variables. Okay, now let's flip to our do file. So this is one way we can do this. Another way to get the numerical summaries for the continuous or quantitative variables is to use the univar function. The univar function basically generates univariate summary statistics. Okay, so we can get that for sepal length, sepal width, petal length, and petal width. Okay, so let's highlight this and run Control D. Let's flip to our result window. So what do we see? So we can see the same info here. That's the numerical summary. Right, you can see the mean, the standard deviation, as well as the quantiles. Okay, now let's say we want to get a summary statistic for this continuous variables across the levels of the species. Then we can use the univar function. So let me copy this. So now I want to get let's say summary statistics, okay, for the quantitative, quantitative, for the quantitative variables across the levels of the species. Okay, so I can introduce another argument by species. So once I execute this, let's see a threat. So once you flip to a result window, we can see that this is giving us a numerical summary for this for all the variables for the Virginica species. You can also see that. Let's scroll up. You can also see that for versicolor, and we can also see that for setosa, right? So we are good to go. Now this fortunate for us, we can see that these variables are all in the same unit of measurement. Sometimes the variables that you have at hand may be in different units of measurement. Okay, this may be in centimeters, this may be in kilograms, this may be in dollars, this may be in different units. So in that case, if you are trying to use some algorithm, especially machine learning algorithm, you may not get a result of interest, right? Because they are not on the same scale of measurement, right? So in that case, what we normally do in statistics is to basically transform or pre-process our variables by either standardizing it or normalizing it. Okay, so let's look at how we can pre-process. So let's look at data pre-processing or transformation. Okay, so this is very important for some machine learning algorithm or some model that you want to make use of. Sometimes if you use the original unit of the variables, you may encounter some challenges. Okay, you may not even get a result of interest, but if you try to pre-process or transform these variables so that they can be on the same scale of measurement, then you will see the real result that you actually want to see. So we can pre-process or transform our variables by either standardizing it or normalizing it. A standardized variable is a variable that has been rescaled to have a mean value of 0 and a standard deviation of 1. Whereas a normalized variable is a variable that has been rescaled to have a minimum value of 0 and a maximum value of 1. Okay, so let me show you the formula for that. So for standardization, this is the formula. We are going to basically compute the mean value for each variable, subtract it from the data point, okay, and divide everything by the standard deviation of the variable. Whereas with normalization, we are going to compute the minimum value for the variable, subtract it from the data point, and divide it by the range of the variable, which is the maximum value minus the minimum value. Okay, so let's go back to our do file and see how we can pre-process or transform our variable. So we want to start with that of standardization. Okay, so I want to start with standardization. So method 1, standardize variables. So I want to standardize our variables so that they can be on the same scale of measurement. Okay, so we are going to basically use the generate function. Okay, so let's say we want to generate a new variable known as z underscore xl. So this is a standardized variable for sepal length, right? So let's first of all get the mean and the standard deviation. Okay, so I'm going to use the sum function, sum of xl sw, that is sepal length, sepal width, petal length, and petal width. Okay, so this is to forward to get the mean and standard deviation. Okay, standard deviation. Okay, so let's execute this. Control D. Let's flip to our result window so we can see the mean value for sepal length, right, as well as standard deviation. So we can now start with the standardization. So we are going to compute the sepal length minus the mean value, which is 5.8541. Okay, and let me close this and divide everything by the standard deviation, okay, which we had 0.8238. Okay, so let me copy this, right, and paste. So I'm going to change this to SW, that is standardized variable for sepal width. So this should be SW, and let's look at the mean value for sepal width, 3.060, and you see the standard deviation too. Okay, so let's replace that. So we have 3.0601, and the standard deviation is 0.4378. Okay, let me copy this too and do same for the petal length and petal width. So let me change this to PL, right, change this to PL. So the mean value and standard deviation, so that's the third one. Okay, so we have 3.7669, and the standard deviation is 1.766, right, 7602. Okay, then let's do for that of petal width. So change this to petal width, so the mean value and standard deviation. Okay, now the last one. So we have um, um, 1.22020. Okay, then the standard deviation is 0.7598. Okay, so we are good to go. So let's execute this. Okay, so Control D. Now let's use the describe function to get a structure for a data set. So this Control D, let's flip to our result window so we can see that we have added the standardized variables to our data set. Right, so we can basically summarize this to see get a summary statistic for it. So let's use the univar function and say we want z underscore xl, z underscore sw, z underscore pl, z underscore pw. Okay, so let's execute this. Control D. So let's flip to our result window. So we can see that for standardized variable, the mean value is going to be 0 and the standard deviation is 1. Okay, now let's do same for the normalized variables. So let me copy this. Okay, want to do for the normalized variable, so paste. So now I want to get the minimum cause. Okay, get the minimum and maximum values, max values. Okay, so let's execute this. Control D. Let's flip to our result window. So I'm going to make use of the minimum and maximum for the normalization. Okay, so this is for sepal length. Okay, so let me change this to normalization or normalized variables. Okay, so change this to 2. Then we want to change the name. Okay, so let me change this to n, change this to n, and change this to n. Okay, and now we are going to make use of the minimum. Okay, So the minimum value was given to be 4.4, right? And we are going to make use of the range. So we had 7.9 minus 4.4 for separ length. Let's look for that of separ width. So for separ width, we have 2 4.4. So we have 2, right? Then we have the range to be 4.4 minus 2, okay? Let's see that of petal length. So petal length, here we go, 6.9. So I'm gonna say 1. Then the range, let me drop this. So we have 6.9 minus 1, okay? Then for that of petal width, we have this 0.1, 2.5. So let me scroll down. So I have 0.1, 0.1, okay. Then we have 2.5 minus 0.1, okay. So I think we are good to go. So let's try and highlight this and execute Control D. Right, once we are done, let's get a description, structure of our data set. So we have added the normalized variables as well. So we can see it in our data set now. So let's try and get the summary statistic for the normalized variables. So let me change this to n, normalized variables, n, okay. So let's get the summary statistics, Control D. Let's see the results. So for normalized variables, the minimum value is going to be 0 and the maximum value should be 1, okay, approximately 1, okay. So I think there was a mistake here. Here should be 7.9, okay. So let's rerun this and let's see the result again. Control D. So it should have fit it, okay. I think first here should have been 7.9. I made it 7.0. So for normalized variables, you always have a range of value. The minimum value is going to be 0 and the maximum value is going to be 1, okay. So we are good to go. Now let's move to the second part of our data summarization, which is how to get a summary statistic for the qualitative variable. So for qualitative variable, categorical variable, we use the table function, tabulate or the tab, right? In short, tab of the species, okay? So we are going to get a frequency table for this variable, okay? As I've already explained, for categorical variable, frequency distribution is one of the ways we can basically use to describe our categorical variable. So let's highlight this, Control D. Let's flip to our results window. So we can see that for this variable species, the label for setosa, versicolor, we have the frequency for each of them, as well as the cumulative frequency, the cumulative percent, right? So this is basically how to describe your categorical variable by using the table or the tabulate function, okay. So we are good to go. So in our next tutorial video, we'll be looking at how to do the second aspect of the EDA, which is data visualization. I hope you stick and stay.